Okay, I've gone ahead and cleaned up some of the code, and I pulled all of the inputs over to this side. So I pulled them out of some of these boxes. And I'll zoom into these various sections so you can just kind of compare your code to what I've done. So we obviously defined the shape of the truss, but it's 3 top chords or 3 top points on the top chord, 2 bottom points. And we sliced it up with planes, and then we went off and pulled all the segments out that we got out of that. So that gave us a relatively straightforward method of making a truss system. And then we created both a load preview, and I'll zoom in here so you can see what this looks like again. The load preview, which it doesn't come off of here for the actual loads. We're actually stealing it. Where does it show it coming down here? I'm not seeing the loads attached to. Oh, that's because they're coming in here. So there must be some place that I grabbed them down there. Anyway, so that's just the loads preview. Our supports, we're taking our supports and putting them down into our analysis. And then down below here, we're getting into our analysis. And if I pull this whole thing off to the side, and I'll just zoom in on our sliders, I think this is a just great chance to experiment around what we've actually created. So we can control the length of the truss. We can make it longer, and as we do, we see a little more deflection in the truss system, from basically looking like nothing to seeing this appearance of some deflection here. And if we make the truss shallower, you'll notice that the truss loses its strength. So here we have extremist amounts of deflection happening when the top chord and bottom chord are offset a little bit. We can see what happens if we add truss segments to it and whether it gets stiffer. And we have obviously this support over here on the side. And we can then reduce the weight just gives us a way to modulate how much deflection we actually look at. And we can pull the second support in or out depending on how we choose to do that. So we'll actually offset the top chord a little bit so it behaves a little stiffer. Whoops. Let's pick a medium range value here. And the other thing that we can do is actually bow this truss, which is a nice feature. So we can continue to go up and make it, a bow truss for a roof system. So there's a lot of interesting things that can be done here, changing segments, how long it is. And with that in mind, we'll move off now to actually being able to visualize this idea of the whether an element is in tension or compression. So we have this output of our geometry, and we're going to make a section, I'll call it evaluate strain. So we're going to, let's take a look at what these geometries look like. I'm going to make a watch list. So these are the deflected geometries, not the original geometries. And it turns out to be a list of lists. So the first thing I want to do is I just want to make it a much simpler list. So I'm going to go ahead and flatten it. So if I pull these geometries into a flattening and then look at this list, now we have a list of just lines. So those are those are lines that are the actual deflected lines. And if I probably accentuated this a little more, let's go back and do some adjustments to our truss as we work through this. I'm going to make the truss a little bit shorter so it fits on the screen better. I'm going to take the bow out of the truss, and the 9 segments is fine. And I'll put a little more weight in so we can actually see the deflection. And we'll deal with it as a simply supported beam. So I'll put this other support all the way out at the end, which happens to be 9. So now we have a pretty good visualization of a truss and its deflection. So we have this idea of a starting geometry and then a deflected geometry. And those are by connecting the nodes together with how much each element has elongated, and you get that appearance of the deflection. So we have those lines, and we also have the lines, and I'm going to just copy the list flatten again. And as I said, we also have the lines for the starting geometry. So if I highlight this, you'll see that's the flex geometry. And if I go back over here, and look for this geometry, I believe it is. Let's plug that in. That's our starting geometry. I'll move this green thing out of the way. So we have both the A and the B geometries, so we can use those to compare whether the component has actually gotten longer and or shorter. And we have a tool that'll help us do that. I'm going to pull the watch box off a minute. And it's under geometry and it's curve. We can evaluate the length of a line, but we'll just deal with it as a curve right now. We'll call it a curve. And what we want to do is find its length. So let's see if I can find this quickly, just going through the list. And this is quite a list here. So I'm not finding it. Segment length at parameter. I'm not finding it easily, so I'm going to just type in curve length. And it was just under length. And so if we put this in and a curve, what we're going to get out is a value. So we get either, these are all the ones that are 10, and they're either a little bit shorter or a little bit longer depending on how they're deforming. And we're going to duplicate that and actually grab the same thing off of the original one. And I don't know where that came from, so I'll just remove it. Okay, so now we have this idea of both a length of an A and a B. And what I want to do is find the difference between these two. And just for the sake of the way I've organized this in my code that I've already written, I'm gonna swap these this way because I've got a code block that I'm going to put in here that takes in the data a certain way. So I'm going to grab a code block. And I'm going to take the original shape, and I'll call it O. And I'm going to subtract the new shape to come up with a value. So the original plus the new, and all I'm doing is coming up with now something that is just the difference to change in each element's length. And let me just zoom in here because this is important. Now you'll see that they're either positive values or negative values, which means the length of the element either got shorter and or longer. And right now we want to pull off some information in one of two ways. We want the absolute change in this to show the significance of the stress or strain, or excuse me, the compression or tension on the element, but we don't want to deal with the negative. So one of the ways to deal with that is to do an absolute value. So under math, I think we have, see if I can find that quickly. Math, we have a concept of absolute value. I'm not seeing it. Oh, here it is. Absolute value. And we're going to go ahead and plug that in, and I want to just show you quickly how that works. Put the absolute value in now, and all the numbers are positive. So we just have the absolute, the negatives are gone. We don't know, now we've actually lost information because we don't know if it's absolutely, if it's a tension or a compression element. But that's okay because all we're doing with this is just assigning this to a cylinder. We want to make a cylinder around each one of these elements. So I'm going to look for a geometry and a solid and a cylinder, and I want it to be with the radius. And I don't want to start an endpoint. So let's see. Here's one. Oh, I'm not finding it. Let's just delete these two. And I'll do cylinder by curve. And there it is down there, cylinder by curve. And that it's in a custom node, so that's probably, I don't know if that's a Dyna shape or some other, but it's very handy. I hope you guys have loaded that in. If not, we can discuss when we get there how we're going to do that. So our path is, to start off with, is our well, we could just put anyone in for this evaluation. So we're going to add a cylinder by curve by path, and we want, if I plug in this absolute value into the radius, all right, we're actually getting the effect. If you look back in here, you can see how we've got this, these top elements are really thick, the bottom elements are really thin. The amount of activity that's happening is different towards the edges as it is in the center. In this place, you get thicker towards the edges. So there's a lot of things going on here that are changing that. But what I'd like to do is actually make that a little more controllable. So we're going to actually remap that number. So what that means is I'm going to change. I'm going to take the numbers that are coming off of this. If I put this into the watch list, right? These are all go from really small items to relatively large items. So we've got from almost a factor of 100 of change, and we probably want something that's just a little more subtle than that. So I'm just going to remap all the numbers using a function called math remap. So let's grab that up. Math.remap. And you can see actually from this this diagram, the blue is kind of how it is right now. It's got a wide range, and we really want to have it a little more subtle range. So I'm going to grab that math remap. I'm going to feed in the numbers, and then I'm going to make a code block that can give me the ranges that I want it to be within. So they'll all be just tamed down a bit, so to speak. And so that code block will be, we right now have 0.01 to, I think I need a 0 in front of this. To 0.1, and we'll feed those in. And now our math range, if we connect this up, oops, all fits within a tighter set of parameters to it. And so I'm going to feed that into the radius. And you'll see how that works out a bit as we go along here. But that gives us control over the diameter of our cylinders. And now the next thing I want to do is add some math or some evaluation to find out if it's in tension and or compression. And then with that, make a decision on what color to make it. So we can actually have a nice function for doing that. We have a if-then statement. So I'm going to go if, it's under logic. Let's actually see if we can go and find it here. Math logic, yep. And or operators, nope, logic. Well, that doesn't give us the full range here. So I want an if, and I want it to do a few things for us here. So I want it to be a test. Let's see what happens if I select this one. There we go. So if that number is true to the test, then make it something. If it's false, then make it the other thing. And the thing we're going to make it is just two different colors. So we're going to build up a code block. And actually, I'll just copy down a code block that we've already made here. Here's a color code block over here. I'll do Control-C to copy it. And come over here and paste it. And this one, we want it to be actually a red one. And we want it to be full density. So let's go 255. That makes it not any transparency to it. And we want the color to be 255. And we'll feed that in. So we'll make it one color if it's true, and we'll make it another color if it's false. And the other color we're going to make it is red. So this is actually green, and so this one will be red. So put 255 in here for red, and 0 in here. And now let's go through the idea of what we want as far as a piece of logic. And really the idea is whether it's a positive or a negative value. So I'm going to make a code block again. And we're going to put in x, which is the number. And if it's greater than, I got to find my greater than symbol, greater than 0, then it will be true. And if it's not, it'll be false. So that's our test. Let me wire up our false. And now all we need is that idea of our logic to input with that. And that's coming right out of here. If I plug this into our watch box, you can see again, our code block is either giving us positive or negative numbers. So I'm going to connect that as our input here, or try to without making a mistake this time. And we have 37 trues and falses. And now we just really can't visualize it because even though we've assigned these colors to it, you see it's either red or green or assigned to it. We need to actually give the geometry the color. So we already have the cones created, and now we just want to color them. So we're going to go geometry, color. And we can plug our color in, and we can plug our geometry in, and we should be getting, I'm not getting, let's see what's wrong with our numbers here. I'm not getting red. And that might be because it's overwritten by the preview. So let me just turn off the cylinders altogether. Yeah, that's what's happening. And if we zoom in here now, we can see which elements are under tension and which elements are under compression. And the only thing I don't like is that these really aren't very significantly large elements. So that's a review of this. And I'm going to now just group, or I review a dialogue of how to create this. I'm going to group these all together again. And call this evaluate strain. And the only other thing I'm kind of unhappy with now is that we really don't have, in this math remap, I'm not exactly happy with these value systems. So I'm thinking that maybe I want to change these a little bit. So I'm going to zoom in here. I'm thinking maybe that if I made this 0.1, let's say to 1. Now our elements, now you can see how our elements get really huge. So that's excessive. So let's pick something at 0.05, and we might leave that at 0.1. Oops, I need a 0 in front of this. Oh, well, 0.1 doesn't make sense. 0.5 is what I want. Let's delete that. All right, so hopefully you're getting the idea there. So now we can control the significance of the thickness of our elements that we're expressing basically by the size of the cylinder, how much stress is on each component. So let's go now and back off on this, and then we can go ahead and play with it a little again, once again. I'll zoom in here. We can make our truss a little bit longer. It's not going to affect, it'll still be able to do the calculations, but you'll notice how it's deflecting differently. Let's see how it works with bowing the truss. That's pretty interesting. We have a compression element on one end and a tension element on the other one. And maybe if we went to more equal number of segments, let's see if we go to 10. No, we can't. I don't know if we can ever get to a... No, that looks a little bit screwy to me. Whoops. If we have 8 truss, we can't go over a certain number because we only have the second support at a certain place. Truss segments at 7. Let's go to 8 here. And let's see what happens with a bow truss if we move in our second support here. All right, so I mean, this all makes sense because obviously this is carrying load and is pushing these things into compression like that. So I think it's a really kind of a fun project to go through and see what, see kind of a representation of the stresses that we, or the stresses and strains that we put on a truss system. Let's make this, I'm thinking about making this a little bit shorter now. There we go. So for finishing this up, I would want us to obviously have some nice clean code and then run some variations of our evaluations of the truss. What I'm going to do after this is probably look at another object to put here. Instead of using a cylinder, we could probably just put a flange here. It really doesn't make sense to, these look too much like their actual construction elements. And we might want those to just always be tubes, but we may want to have something coming off of this like an extrusion that shows us how much stress or strain is on each component. So I'll try that out in the next clip.